Bismillahirrahmanirrahim. Assalamu alaikum, students. So we are today ready with another lecture. Today's lecture, we will discuss the idea of cyclic coordinates. Let me write cyclic coordinates. What are cyclic coordinates? Let us discuss that. These cyclic coordinates are also called sometimes ignorable coordinates. So let us discuss. We know the form of Euler-Lagrange equations. Let me write them. Dou L by dou E Q dot. Then we write its time derivative and equate that to dou L by dou Q K. This here dot. This is the Euler-Lagrange equation written for a generalized coordinate QK, right? Now, if the Lagrangian of the system, let me write it in another color. If the situation is such that the Lagrangian of the system doesn't depend on this coordinate QK, if the Lagrangian of the system which is under consideration, Lagrangian does not depend on this generalized coordinate QK, then dou L by dou QK is 0. Let me adjust my pen. This thing is 0. Where if we say that Lagrangian doesn't depend on the particular generalized coordinate, then its partial of the Lagrangian with respect to that particular coordinate is 0. And when we use this condition in the above Euler-Lagrange equations, what we get d by dt of dou L by dou QK dot is equal to 0. What does that mean? That means this thing, let me use another color. This dou L by dou QK dot is conserved in time. Conserved in time. So it will not change with time. Now what is dou L by dou QK dot? It is the generalized momentum corresponding to the coordinate QK. So when this happens, we call such a coordinate, generalized coordinate, as cyclic coordinate or ignorable coordinate. right? So if there is some coordinate on which there is no dependence of Lagrangian, then the partial of Lagrangian with respect to that coordinate is zero, which implies from Euler-Lagrange equation that the time derivative of the generalized momentum corresponding to that coordinate is zero. That means that generalized momentum is independent of time. So such coordinates which we here consider QK are called cyclic coordinate or ignorable coordinates, right? We'll consider some examples and we will see that the generalized momentum corresponding to some generalized coordinate does not necessarily have the unities of linear momentum. Sometimes it can be linear momentum. Sometimes this generalized momentum corresponding to some coordinate can be angular momentum as well. So let us discuss an example. Let me name this example 1. The example goes like this. Consider a ball thrown through the air in the full three dimensions full three dimensions the Lagrangian of the ball is given by. Let me write the expression for the Lagrangian. It is simply half m times x dot square plus y dot square plus z dot square. This is the kinetic energy term. Then I have the potential energy term minus mg z. So this is the Lagrangian of this ball. Remember the coordinate system which we have taken. We have taken Cartesian coordinate system like this. This is my x, this is my y, and the vertical direction we are taking z, and this point is the origin of my coordinate system. So when I throw this ball in three dimensions in Cartesian coordinates, the Lagrangian is written this way. The potential energy term is mg z, where zero of the potential energy is taken when z is 0. When z is 0, mgz becomes 0. That means 0 of the potential energy taken at z is equal to 0, right? So we framed the Lagrangian and we can see in this Lagrangian there are three terms pertaining to the kinetic energy. One is the kinetic energy corresponding to motion along x direction. Second is the kinetic energy pertaining to motion along y. And third one is the kinetic energy pertaining to motion along z. Now we see there is no x or y dependence here in the Lagrangian. Let me use another color. So there is no x or y dependence or y dependence in the Lagrangian L. What does that mean? That means dou L by dou x is 0 and dou L by dou y is 0. That means x and y are cyclic coordinates in this situation, are cyclic coordinates. That from Euler-Lagrange equations means, let me use the another page. That means from Euler-Lagrange equation, when you write it for x, d by dt of dou L by dou x dot is 0 and d by dt, when we write Euler-Lagrange equation for y of dou L by dou y dot is 0. That means dou L by dou x dot, dou L by, sorry, not d, dou L, let me clear it. Dou L by dou x dot is conserved in time. It doesn't change with time, in time. And also dou L by dou y dot is conserved in time. It is not going to change with time. What is dou L by dou x dot? It is the generalized momentum pertaining to the cyclic coordinate x, and dou L by dou y dot is the generalized momentum corresponding to the cyclic coordinate y. Now from Lagrangian, if you find it out, you find the partial of L with x dot. What is that? That is mx dot. So my dou L by dou x dot, I will change the color here. My dou L by dou x dot is mx dot. And my dou L by dou y dot is simply my dot. You can see simply this is the linear momentum, mx dot is the linear momentum in x direction, and my dot is the linear momentum in y direction. You can see it is simple to justify, since there is no force on the ball in x and y directions, therefore the momentum along x and y directions are constant in time. They are not going to change with time. Now, we say it in classical mechanics this way. We see that the conservation of mx dot, that is the linear momentum along x direction, arises from the spatial translational invariance in the x direction in the Lagrangian of the system. I repeat, we say that the conservation of mx dot, that is a linear momentum along x direction, arises due to the spatial translation invariance in the x direction of Lagrangian of the ball. That means if you throw a ball at one x coordinate or some other x coordinate, that is not going to change the physics of the ball because the Lagrangian doesn't depend on x. That leads to the conservation of linear momentum along x direction. And similarly for y, y is also a cyclic coordinate. So you throw a ball at one coordinate into the air or some other coordinate, other y coordinate, Lagrangian has this spatial translation invariance in the y direction also. Physics doesn't change, so the linear momentum along y direction is also conserved. So this is the advantage of using generalizer coordinates, but we have to choose them properly or using some clever guess so that we can see the conservations inherent in the system easily. You can see here when we write Lagrangian in Cartesian coordinates, from the idea of these cyclic coordinates, we can easily see which quantities are conserved in the system. Let us do another example. Let me write example 2. Consider a potential that depends only on the distance to the z-axis z-axis. Now in cylindrical coordinates, let me adjust my pen. In cylindrical coordinates, the Lagrangian of the system or of some mass m is given by, let me use another color. L is half m r dot square plus r square theta dot square plus z dot square minus v of r. So we're considering the motion of a particle having mass m, which is moving in three-dimensional space under the action of a potential v of r, which depends only on the distance of the particle from the z-axis. Remember how we define cylindrical coordinates? I will give you a rough diagram. Let me draw it clearly. So we define cylindrical coordinates this way. This is my origin. This is my x direction. This is my y direction. And this is my z direction. So if I have some point in space P, its cylindrical coordinates are denoted by r, theta, and z, where r is the distance of the point from origin. That means if I find the projection of this P on the xy plane, then this distance is r, and this is the theta angle. This is the angle made with this positive x direction. This angle is called azimuthal angle, right? And then there is z. Z is simply the distance of the point along the z direction. This is z. This distance is z, right? And this distance is x from this point, and this distance, when you find, it's actually you have to draw the perpendicular from this point on x-axis, then on y-axis, then the distance is your y. I hope it is clear to you. So r is the distance of the point from the origin. Theta is the angle made with the positive x-axis. As shown in the figure, z is the same as in Cartesian coordinates. So r, theta, z are called cylindrical coordinates. And then we define three unit vectors. Unit vectors are r cap, the unit vector in the direction of increasing r, and then we have theta cap, the unit vector in the direction of increase of theta, and z cap, the unit vector in the direction of increase in the coordinate z, right? R cap, theta cap, and z cap. So now if the particle is moving in space, its kinetic energy has three parts. Half m r dot square is simply the kinetic energy along our direction, and half m r square theta dot square, if you see, it is actually the rotational kinetic energy about z direction. Rotational kinetic energy about z-axis. Theta dot becomes actually the angular velocity of the particle for rotation about the z-axis. As theta changes, the point is actually rotating about the z-axis, and mr square becomes actually its rotational inertia about the z-axis, and theta dot is its angular velocity. So the second term, half mr square theta dot square, is actually the rotational kinetic energy of the particle about the z-axis, and half m z dot square is simply the kinetic energy along the z cap direction, right? So you can see in this Lagrangian that there is no dependence, z dependence in the Lagrangian, and there is also no theta dependence. There is dependence in r, but there is no dependence of Lagrangian on z and theta. So they are cyclic coordinates. So let me write. There is no z dependence in the Lagrangian. That means what? Dou L by dou z is 0. Also, there is no theta dependence in the Lagrangian. No theta depends in the Lagrangian. So dou L by dou theta is also 0. So from Lagrange's Euler-Lagrange equations, what does that mean? That means dou L by dou z dot, which is the generalized momentum corresponding to the coordinate z, is constant in time. It doesn't change with time. And similarly, dou L by dou theta dot, which is the generalized momentum corresponding to the coordinate theta, is constant, right? Now, if you find dou L by dou z dot from the Lagrangian, what is that? Dou L by dou z dot is simply m z dot. Go into the Lagrangian. Dou L by dou z dot is simply m z dot. What is that? That is simply the linear momentum in z direction. So this is a conserved quantity in this situation. The linear momentum along z direction doesn't change with time. And what about dou L by dou theta dot? What is that? Dou L by dou theta dot, when you differentiate partially L with theta dot, you will get mr square theta dot. Mr square theta dot. See the Lagrangian. Dou L by dou theta dot is mr square theta dot. Now see, this mr square theta dot is what? This is the, can you guess it? It is the angular momentum of the particle around the z direction. It is the angular momentum. Angular momentum of the particle around z direction. Because you see, as theta changes, theta dot becomes its angular velocity, mr square becomes its rotational inertia. So mr square theta dot is simply the angular momentum of the particle about z direction. So in this example, you see we have two cyclic coordinates. One is theta, and corresponding to that, the conserved quantity is the angular momentum about the z direction. And you have another cyclic coordinate in this situation, that is the z, and corresponding to that, we have generalized momentum, which is the linear momentum in z direction, which is constant in time. Notice here the conservation of angular momentum about the z direction is, or I should say, arises from rotation invariance around the z axis. Let me go to the figure. If you rotate this particle about the z direction, keeping z and theta fixed, the particle looks the same. I repeat, if you fix r and z, then you change theta. That means you are rotating the particle about the z direction. The system is invariant. It looks the same. That leads to the conservation of angular momentum along that direction. I repeat, the rotational invariance in the system around the z direction leads to the conservation of angular momentum around the z direction. I hope it is clear to you. Now we will discuss another example. I call that example 3. In spherical coordinates, consider potential that depends only on r and theta. Now you know our convention for spherical coordinates is that theta is the angle down from the North Pole, down from the North Pole, and phi is the angle around the equator, around the equator, equator. Let me draw a simple figure. You know it already, we have discussed it already, how we use spherical polar coordinates. But still, to refresh your memory, I will draw a simple diagram. So if this is my x, this is my y, and this is my z. Now I have a point P in the space. We label them with r, theta, phi in spherical polar coordinates. R is simply the distance of the point from the origin. And as I told you, this phi is called azimuthal angles, is the angle around the equator, and theta is the angle with the positive z direction, or we say it is the angle down from the North Pole, right? Then we define, as you know, the unit vectors r cap, theta cap, and phi cap. They are the unit vectors in the direction of increase of the respective coordinates. Now, situation is we use spherical coordinates and we consider a particle moving in space under a potential that depends only on r and theta, not on phi. So what is the Lagrangian in this situation? The Lagrangian of the particle is, let me write it, half m r dot square plus r square theta dot square plus r square sine square theta phi dot square. This is the kinetic energy minus the potential energy, which we say depends only on r and theta. Half m r dot square plus half m r square theta dot square plus half m r square sine square theta pi dot square. Check it at home. This is your one of the homeworks. I'll use another color. We have done it in the previous classes. Still, you check it. Check it at home. So if you see here, the first term in the kinetic energy is simply kinetic energy in r direction. Then the second term is actually the rotational kinetic energy. About which direction? About the rotational kinetic energy about the x-axis actually. Because theta is the angle with, so as theta changes, theta dot becomes the angular velocity. So m second term becomes the rotational kinetic energy about the x direction. Then if you see the another term, third term, that becomes as phi changes, phi dot becomes the angular velocity due to the change in phi. So the third term is basically the rotational kinetic energy of the particle about the z direction. Check it. Now there is no phi dependence. There is no phi dependence in the Lagrangian. That means dou L by dou phi is 0. Phi is a cyclic coordinate. What is the conserved quantity corresponding to this cyclic coordinate? That is simply dou L by dou phi dot. So dou L by dou phi dot will not change with time in this situation. And from the Lagrangian, if you find this partial derivative, it will turn out to be mr square sine square theta phi dot. Mr square sine square theta phi dot. If we check, it is simply what? It is the angular momentum, angular momentum of the particle around the z axis, around the z axis. So in this case, angular momentum around the z-axis will not change with time. It is a conserved quantity because phi is a cyclic coordinate. If you compare the previous example with this example, you see here the system is has this rotational invariance about phi. That means if you keep r and theta fixed and you change the phi, what will happen? The system will look the same. Situation will be similar. So there is rotational invariance in the system about the z direction. So that leads to the conservation of angular momentum about the z axis, right? So I stop here. I hope it is clear to you. So in this lecture, we discuss these. So if we have a coordinate in which there is no dependence of Lagrangian, if Lagrangian is independent of that coordinate is simply the cyclic coordinate, and there is a generalized momentum corresponding to that coordinate which doesn't change with time. This was the summary of today's lecture. Don't forget to like, share, and subscribe my channel. Thank you. You can give comments in the comment section. You can have queries. I will try to answer them. Thanks. God bless you. Assalamu alaikum.